Thanks very much, John, and good afternoon, everyone. Not so much a newest departure. I think I've been working on this for about 10 years. So I'm aging very rapidly as a result of doing it, I must say. So what I was asked to talk to you about this afternoon is best practice for estimating soil nitrogen supply. And I'll give you a brief overview of what I'm hoping to cover this afternoon in a very limited time for an awful lot of slides, so please bear with me. So first of all, quick bit of background, and then a look at some recently completed HGCA project work, and lots of new results for you to take in and to take away and look at after the meeting. Then hopefully some best practice advice, some new best practice advice for you on soil mineral nitrogen sampling and all things around that, and some new information about how you can compare approaches to predicting soil nitrogen supply. Hopefully a few key messages at the end to leave you with. So, background. Well, the first of my bullet points is probably a candidate for understatement of the year, or possibly even understatement of the century. But the use of soil mineral nitrogen testing in predicting soil nitrogen supply has been an area of great debate and uncertainty, and certainly I think most of us probably in the room have been involved in that at some point or another. So as a result of that, some reviews were done back in 2006-2007. It was identified there was a need for some new project work to address some of the concerns, to build some confidence in how to estimate SNS, and also to achieve some consensus across the industry about best practice really in this whole area. So as a result of that, one particular project came out of that, and that's 3425, establishing best practice to estimate for estimation of soil nitrogen supply, which was led by Daniel Kindred of ADAS. And I should acknowledge straight away that a lot of the good information that's come out of this project is down to Daniel's hard work, so please remember that. But it also involved NIOTAG, SAC, and a whole range of industry partners in that particular project. Running alongside that was another project led by Ben Marchant at Rothamsted, which was focusing on cost-effective strategies for soil management, cost-effective sampling strategies for soil management. So, as I said, one of the reasons for doing this work was to try and get some consensus across the industry, try and address some of the concerns, bring together some differing views. So it's really important that we had some project groups here, some industry involvement here in terms of consulting with what we were doing. So both projects had steering groups that consisted of industry, of researchers, of practitioners to try and guide the work. There were stakeholder meetings at the beginning of Project 3425 in 2008, and also again at the end of both projects in 2011, which was an opportunity really for the industry to feed in some of their concerns, some of their thoughts on what we needed to do, and also to share some early results in 2011 and contribute to the conclusions that came out of that. And that stakeholder group, or those stakeholder groups, were really, really wide across all parts of the industry, from government through to farmers at the other end. Now, before I start with any data, there's a couple of important definitions I need to get across to you. The first is, what do we mean by measured soil nitrogen supply? Well, the measured soil nitrogen supply is essentially what we're measuring in the autumn or spring, and consists of the nitrogen that's already in the crop, the available nitrogen that's present in the soil, as nitrate and ammonium, and may or may not include a measure or an estimate of mineralizable N as well. Now, what we're using as our definitive measure of SNS is the amount of nitrogen taken up by a crop at or near harvest without any fertilizer applied. And for the rest of this presentation and in the report that you'll see from this project, it's been referred to as harvested SNS. So that essentially means the amount of nitrogen in the crop without fertilizer at or near harvest. And as you'd expect, on the whole, we'd hope that that is roughly similar to the amount that's measured in the autumn or spring, but obviously some cases it'll be a bit more and some will be a bit less. And there will always be some nitrogen left in the soil as well, but for the purposes of today and this project, we are not actually considering that in this particular case. So you'll see me using measured soil N supply and harvested N supply during the course of the presentation. So why are we interested in SNS? What's the point of this project, essentially? And really, the main reason is because SNS, or harvested SNS, is an important potential predictor of our fertilizer N requirement. On these particular two charts here, and this is based on data from other projects, not from this particular project, but we have reanalyzed that data as part of the project. We've presented on the left-hand chart the relationship between harvested in SNS, so our final measure of SNS, against measured N optima in about 53 recent wheat N response data sets. And what you'll see is that harvested SNS explains about 60% of the variation in optimum fertilizer N dose. But there's an important caveat to that, and if you look at the line and the points that are in that chart, you'll notice that the ability to fit that line and the relationship has a lot to do with the fact that we had some very high harvested SNS values there. And if you look at the SNS values below about 100, there's an awful lot of vertical scatter there and not a very good relationship. If you look at the right-hand chart, that's the relationship between measured SNS in the autumn or spring against measured N optimum. And there we're explaining about 40% of the variation in N optima by the measured SNS. And it's similar to the last chart, you can see there's an awful lot of scatter below 100 kilograms of SNS, not a lot of relationship below that level. But the fact is, this is about as good as it gets in terms of our ability to predict fertilizer N optima. Any other predictors look poor even by comparison to that. So we generated some new data in Project 3425, around 180 sites, so we've worked on a lot of sites. You can see where they were in the map on the left-hand side, across 3 years, stretching from the south of England to the south of Scotland, and also the colouring on the map is different rainfall areas, so we were covering low, medium and high rainfall areas. We picked a range of soil types, range of previous crops, a range of manure histories. They were sampled in autumn and spring for SNS, and we did our measure of definitive SNS, our unfertilized sampling at harvest. And you can see in the bottom picture, it's just an example of one of the sites. You see the sort of yellowish square at the bottom, which is one of our sites. So, into some of the new data then. So this is from 164 cereal sites between 2008 and 2010, almost all of them wheat, but the one or two that were barley or oats. And quite a complicated set of charts, so I'll take you through it bit by bit. So on the left-hand side, we have plotted harvested SNS against autumn SNS. And you'll see that you've got a whole load of blue crosses, which effectively each one of those is a site. You have a dotted line, which is the one-to-one line. So any point that sits on that dotted one-to-one line, it means essentially the autumn SNS is the same amount as the harvested SNS. Anything above the line means that the harvested SNS was more than the autumn SNS, measured autumn SNS. Anything below the line, the harvested SNS was less than the measured SNS in autumn. There is another line on there, which is commonly called a broken stick, which has sort of a slope and then a flat bit. That is the split line regression line between the measured SNS in autumn and the harvested SNS. And that split line regression line has essentially 3 different components to it. One is an intercept on the y-axis, on the harvested SNS axis, and essentially that intercept indicates the amount of nitrogen you would have for your harvested SNS, the amount of nitrogen in an unfertilized crop at harvest, if you measured no nitrogen in the soil in the autumn or the spring. And obviously that's coming from things like mineralization and deposition during the season. You've also got a slope, and that represents the proportion of the measured SNS that you end up with in the harvested SNS. And you'll see the slope in the autumn is about 50%, basically 0.5. And then if you have your flat point, you have your broken stick, and that represents the point at which, no matter how much more we increase the measured SNS, on average we don't get any increase in the harvested. There's a limit to how much nitrogen an unfertilized crop will take up, no matter how much is present in the soil, and the fitted limits here are about 200. So the diagram on the right-hand side is much the same, except that's just for spring SNS as opposed to autumn. And you notice that the amounts of the percentage variation explained by the autumn and the spring measured are pretty similar, but there's a small advantage in favour of the spring measure. Now, we can do the same thing without using our measured SNS, but using something like the field assessment method that's present in the Fertiliser Handbook RB209. And obviously here what we've got in RB209 is not a whole range of measures, but we have a series of different indices from 0 to 6. Representing different bands of SNS. So that's why we have sort of, if you like, columns of points there rather than a scatter. But you can put those on a similar chart, and you can see that actually they fit fairly well either side of the one-to-one line. which we'll come back to in a minute. But actually, the proportion of variation explained in harvested SNS is smaller, because obviously you've got stacks of points there. So it's about a 31% of the variation is explained. Now, that's sort of, I feel like, a global overview of all of the data. What I want to know now is to break that down a little bit into some subsets of data. So across the top, where I've put all, you'll see the percentages that I showed you on those last slides. The 45% of variation in harvested SNS explained by autumn SNS measures, 49% for spring, the 31% for the field assessment method. If we now split that up into different soil types, you'll see something interesting. First of all, if you take your silts and your clay soils, you'll see here that the percentages of variation explained are at the higher end, so sort of 50 to 60% by either the autumn or spring. And in fact, the autumn and the spring are pretty similar in the two figures. And they are higher than the field assessment method. So the autumn and the spring on the silt and clay soils measured values are explaining more of the variation in the field assessment method. If you look at the medium soils, you'll see that the proportion of variation explained is falling, so it's less good predictor. But you'll also notice that the spring is better than the autumn in that case, 44 as against 23. So the spring measure is the best one there. If you look at the shallow soils and the light sands rather, what you see is a lot of zeros, a lot of very low numbers. And effectively, none of those predictors, the measured or the field assessment method, are really any use at all in terms of predicting the variation in harvested SNS. They're very poor predictors. That's partly because we had less sites, as you see, smaller numbers, but also because the range of SMN on those sites was smaller. And as I showed you earlier, what really helps in producing a relationship is having a wide range of SMN values. And the SMN values, SNS values, were much narrower on the light and the shallow soils. We can make a similar comparison by rainfall area, and you'll see that the best predictions we get are in the low and the medium, moderate rainfall areas, and there again, they are tending to do slightly better overall than the field assessment method. Once we get to the higher rainfall areas, the predictions become much poorer, much lower numbers. And certainly, the wetter it gets, really, it's the spring measure that stands out, obviously, because the spring is happening after, measures are happening after the winter rainfall period. We can also break down into divide between sites that have got a grass or manure history against those that haven't. And if you do that, you will see that in terms of the comparison between the measured values, the autumn or spring SNS, against the field assessment method, then the field assessment method compares best in sites that have got no grass or manure history, so basically arable situations. Where they've got grass and manure, then the SNS, measured SNS improves the situation. Finally, at the very bottom, which some of you might not be able to see, but it's in your packs, if we divide into normal arable situations, a normal arable situation would be somewhere which has got probably an SNS of less than 100. It's sort of mineral soils, growing arable crops, no manure, no grass in the history. Again, the value of those measures as predictors of harvested SNS are quite poor. The numbers are quite low. And they're much better, really, where you've got the more abnormal situations, if you like, where we've got manures or grass or high-end veg or something like that with high SNS situations. If we look at the impact now of sampling depth, and if we compare, first of all, for the autumn, just ignore the sort of greyed out values, just look at the percentage variation explained by different depths of sampling in the autumn and then the spring. You can see that in the autumn, the highest number we get is at 0 to 60. So essentially, we get no benefit really from sampling deeper than 60 centimetres in the autumn in terms of explaining the variation in harvesting SNS. You can imagine that's why, because nitrogen that's at depth in the autumn below 60 centimetres is quite likely to be lost from the system by the time it comes to the spring. In the spring, it's a different story, and we have to go to the full 90 centimetres in order to get to explain the highest proportion of variation. So, a couple of best practice points for you in terms of when to sample for soil mineral nitrogen. So, overall, sampling in the spring gives you a slightly better prediction of harvested SNS than sampling in the autumn, but actually, as I showed you, on the clay and silt soils, its differences are quite small, and you could do it in the autumn. If you are going to sample in the autumn, sampling down to 60 centimetres is adequate, no advantage to going deeper. If you're sampling in the spring, it should always be down to 90 centimetres. Okay, so we know when to sample. How do we sample? And this brings in some information that's come out of Ben's project, 3189. Using a sort of a standard W sampling design, the sort of thing that traditionally happens on farm, the factors that affect the optimal number of cores to take are the expected amounts of SNS, expected amounts of nitrogen that's present in the soil, and also the field size. So if you look at that sort of matrix, that table matrix there, you can see that the higher the amount of SNS, the larger the field, the more cores that it's justified to take. But for most situations, between about 10 and 15 cores is optimal for sampling. Having taken all of our cores, we put them in a bucket usually, and then we think about mixing them up in order to get a representative subsample. So we had a look in the project about the mixing process, the subsampling process. And there's a couple of sets of things I want to show you on this slide. First of all, we did this on 8 sites, and what we did was we got a sample of soil in the bucket, and some of it we just took basically large quantities out, replicate quantities out, and tested how similar they were to one another in terms of SMN content, and others we did a very careful mixing and subsampling procedure in order to try and get the 5 or 6 samples as similar as possible, and then tested how similar they were between them. And a measure of that similarity is the CV on the right-hand side. So you'll notice that, I haven't got a pointer unfortunately, but most of the values under the heading of thorough are slightly higher, slightly lower rather, than most of the figures under the no mixing. So basically where we did our thorough mixing process, we were reducing the variation within the sort of replicate samples. So we were getting a more, if you like, accurate subsample. But the differences weren't that great, but nevertheless it was significant over all sites. But there was an unexpected effect of this, and that's highlighted by the middle sets of figures, which is the average SMN. And if you compare the figures for the thorough against the no mixing, again you'll see that in a number of sites the thorough mixing figures were higher than the no mixing. So although we were reducing the variation, we were actually increasing the amounts of soil mineral nitrogen present where we're doing this thorough mixing process in a number of circumstances. And you can imagine what's going on there. Basically, by mixing it over a period of 20 minutes, which we were actually stimulating mineralization and increasing the amount of nitrate that's present. So, how to sample? Well, Ben actually looked in his project about different sampling designs, but given all the other uncertainties in soil mineral nitrogen and SNS, there was no advantage to do anything more fancy than the standard W pattern. 10 to 15 cores, generally sufficient to represent a field, and that's actually a bit less than the advice currently in RB 209, so there is an opportunity for a little bit of saving there in effort. If you do have very high levels of SNS, or if you have a very variable site, or the field's very large, obviously it may pay to do more than 10 to 15. If subsampling is required, and it usually is, then you do need to ensure that the sample is representative, but don't overdo it. If you overdo it, you'll simply increase the amount of nitrate that you measure. Now, having got your subsample, you need to get it analysed. So how quickly do you need to get it analysed? So we did an exercise where we took samples and we stored them or delayed the analysis of them for different periods of time and kept them at different temperatures to see what the impact on the measured SMN values was. And so we've got results from 4 different experiments there. In 2009. We did another 4 in 2010, giving us 8 in all. And 4 sites, and we took samples and we tested them at various intervals after sampling, anything up to 14 days, and we kept some of them in a refrigerator at 2 to 4 degrees, which is the current advice. Some of them we just kept at room temperature. And the important thing to notice is where the lines are going. All the lines are going up from left to right. They are rising, apart from 1, but 7 out of 8 are. And so what's happening there is with the delay in the delay in extraction after sampling, delay in analysis after sampling, the levels of SMN in the samples are increasing, and in some cases increasing quite steeply. That's true even when we stored them refrigerated at 2 to 4 degrees. I think there's been a perception in the past that by putting them in the fridge you can keep them there as long as you like and they'll be fine. That's not true. It's still really, really important to get them analysed quickly because it's increasing even in the fridge, but increasing faster outside. Now, for long-term storage, in the past, sometimes we've used freezing as a method of storage, And if you look at the figures under the nitrate column, this is where we stored samples for 14 days, either frozen or in a fridge or at room temperature. You can see, yes, if we froze them, we had lower levels of nitrate in the sample. We prevented the increase in nitrate, but we just got higher levels of ammonium. So we were still getting the mineralization, just wasn't being converted from ammonium to nitrate. So freezing is not the answer. We just shift the problem from one area to the other, and the actual amounts of SMN measured was similar for frozen and fridge stored over that 14-day period. So freezing is not the answer. Rapid analysis is the answer. So just to sort of summarize those points as well, really important that, that we get samples analysed quickly, because there is an increase with delay analysis, even if you store in a fridge. And we've calculated that to be over 0 to 90 centimetres, something like about 2.5 kilograms per day, which might not sound a lot, but it's quite easy to see how if you got samples taken on a Friday, didn't get them analysed until the Monday, had them in the fridge in between, you could easily end up with around 10 kilos a hectare more being measured than was actually present when you sampled. Still important to keep them cool, obviously, because at room temperature the increases are larger and more variable. And freezing really isn't an answer, unfortunately. So having hopefully got the samples to the labs as quickly as possible, we then worked with 3 of the main directly, 3 of the main labs doing soil mineral nitrogen testing analysis, and also we used data from another lab as well, which we were provided with, and looked at the variability in the test results on sort of replicate samples between labs, both between labs and also when we sent duplicate samples to the same lab. As I say, this operation was done with the involvement of the labs, and in fact they were already doing these exercises themselves, so a very proactive approach from them. And what I've done on this chart is we've plotted essentially on the bottom axis you've got the average site soil mineral nitrogen for each sample, and on the y-axis you've got the results from the individual values from the individual samples. So you've got anything between 3 and 6 individual values plotted against the average along the bottom. And you can see that the dotted line is the one-to-one line. So what we'd like to see is all the points obviously on that one-to-one line. And they all fit around the one-to-one line. And in many cases, they all fit quite closely to it. And there is no systematic separation between the labs, and there's as much variation within a lab's 2 samples, for example, as there is between. But there are a few exceptions. Unfortunately, I haven't got a pointer, but if you look at a point around 75 kilograms there, you will see there's one particular example where the 3 labs clearly separated out in terms of the values they were getting. And if you look at, for example, at lab 3 in 0708, which is the hollow blue triangles, you can see most of the hollow blue triangles sit well above the one-to-one line. So in that particular lab was measuring slightly higher levels than the average of what everyone else was measuring. So that exercise is important, and it's been a useful benefit, and has helped the labs, and they're working together now to ensure consistency of results. So given all the other uncertainty, all the other variability that exists in soil nitrogen testing, that those differences in the labs were actually quite small, but ongoing ring testing between those different labs is really important in order to maintain and prevent systematic variation. We did look at whether or not using bulk densities specific to different soil types improved the calculation of SNS, but actually the differences were very, very small, very little improvement. So the standard bulk density, which is currently used by most of the labs, is fine. We've also looked at additionally available nitrogen, which is basically a prediction of how much nitrogen is going to become available through mineralization during the spring, and a calibration of that in terms of what's available. And we did see that improved prediction of the SNS, and I'll come on to that a little bit more in a moment. So, how do we interpret SNS measures? Well, I think one thing that became abundantly clear from the project is that sometimes you'll get very large SNS estimates where you've measured very large levels of soil mineral nitrogen. It's very clear that these can over-predict the amount of nitrogen you get into your crop at harvest, so they can over-predict the harvested SNS. Equally, where you measure very low levels of SMN in the spring, or have a very low SNS, measured SNS, then that can under-predict SNS at harvest. And our advice really based on this is that where you get an estimate exceeding 160 kilograms of measured SNS in the autumn or spring, then treat it as an estimate of 160. Don't go higher than that. Where you get an estimate of less than 50 kilograms of N in the autumn or the spring, treat it as an estimate of 50. Don't go lower than the 50, unless your field experience shows otherwise. It's also clear that SMN measures in the autumn tend to overpredict harvest in SNS. That's because we have things like rain in the winter, most winters anyway, which cause leaching and reduces the amount of nitrogen available. Or indeed, we may have an inefficient recovery of some of the nitrogen that's present at depth in the autumn. Equally, SMN measured in the spring tends to underestimate harvest in SNS. That's because in the spring we haven't had any mineralisation yet. Obviously, that's usually still to come at the time we're doing our SMN measures. So we may need to adjust spring measures for N deposition or for mineralisation. Now, a particular element of what we looked at, and very, very relevant to this autumn in particular, was how to take account of the nitrogen that's present in the crop. In particular, how to take account of the nitrogen that's present in a crop of oilseed rape. So to look at this, we identified and set up crops of oilseed rape in the same field which had small and large canopies. We generally did that by engineering it, and we used a range of techniques to avoid biasing the results. So we used low and high seed rates, we used sort of hoeing out of plants, and we also used overwinter fleece as a way of creating big and small oilseed rape canopies in the same field. We've got something like 28 comparisons over 3 seasons. We measured soil mineral nitrogen, we measured crop, canopy, N at various times, and then we used, again, as our definitive measure of SNS, the amount of nitrogen in the crop near harvest in unfertilised plots. This graph here explains some of what we saw. So, go through it because there's quite a lot of information here. On the bottom, you have your small crop on the left-hand side, and you have your large crop on the right-hand side. The y-axis is the amount of nitrogen present either in the crop, which is the lighter colour bits of the bars, or in the soil, which is the darker colour bits of the bars. And this is sort of an average over 28 sites over 3 years. So let's start with the 2 bars that are headed summer. So if you look at our summer, this is essentially our harvested SNS. Look at our summer bar for our large crop compared to our summer bar for our small crop. Where we had a large crop in the autumn, we ended up with numerically slightly more nitrogen in the crop at harvest than we did where we had a small crop in the autumn. But that's only a numerical difference. It's not a statistically significant difference. And in fact, the range of nitrogen values, harvested SNS values rather, in the large crop in summer was similar to the range that we had in the small crop in summer. If we look at the bars headed autumn, you will see that, again, our large crop in the autumn, not surprisingly, had more nitrogen in the crop than our small crop. That's why it was the large one. But actually, there was slightly less nitrogen in the soil under the large crop in the autumn than there was under the small crop in the autumn. And again, if you think about it, that's quite logical. It's been taken up by the crop in the autumn. It's not going to be present in the soil anymore. And although there's a numerical difference there, again, that wasn't statistically significant. Where we did see a difference was in the spring. And if you compare the 2 bars titled spring, you will see that we've got significantly higher amount of nitrogen, a higher amount of SNS in the spring, where we had a large crop in the autumn, than where we had a small crop in the autumn. And that's because we've got more nitrogen in the crop, and the amounts of nitrogen in the soil are similar. And if you look at the amounts of nitrogen in the soil, compare it for the small crop between autumn and spring, compare it for the large crop between autumn and spring, in other words, compare the 2 sets of the darker bars, you can see that in the small crop, the amounts of nitrogen in the spring, amounts of nitrogen in the soil are falling more dramatically than they are where we've got the large crop. And that's because we're losing more of the nitrogen of the small crop because it hasn't been taken up by the crop canopy. So that's an important message in its own right about the value of a large crop in avoiding losses of soil and nitrogen from the soil. So how do we interpret that in terms of practical advice? Well, what it says is that we know already that crop N needs to be estimated at the time of soil mineral nitrogen, including time of sampling, and included in your estimate of SNS. But there's no evidence that differences in crop NNLC rate should be treated any differently to that in wheat. And certainly it indicates that nitrogen present in RC rape is used very efficiently, it's remobilised in the plant, and we don't actually lose much from dying leaves. So we can treat it the same as we would if it was a wheat crop. Right, this is the most tricky bit, and although the clock is counting down, I think it started counting down a bit early, according to my watch. So I'm going to take my time. So, how do we compare SNS predictions? Well, there's three ways we can make a comparison. Firstly is on their accuracy. And the accuracy is the difference or the bias, in other words, between the average predicted SNS and the average harvested SNS. And the main point to recognise here is that profit is maximised when we have a small negative bias. And that's essentially because there's a bigger penalty if you under-fertilise than if you over-fertilise your crop. The financial penalty, that is. Precision is another way which we compare things, and essentially that's just a measure of the frequency with which our predictions were right or wrong. The third way we have compared approaches is based on profit foregone, and that's the difference in margin over cost if we'd applied nitrogen according to our measured SNS value or other predictor compared to the margin we'd achieved if we applied it according to the actual harvested SNS. And that profit foregone calculation used a grain price of £150 a tonne and a fertiliser price of £300 a tonne for ammonium nitrate. And it's very important to recognise that the cost of soil mineral nitrogen sampling analysis is not included in these calculations. So it's before the cost of sampling and analysis. So this is a pretty scary table. So we'll try and take it little bit by little bit. On the top, across the top heading of my table, I've got your three measures: the accuracy, the precision, and the profit foregone. On the left-hand side, we've got our various different prediction approaches that we've compared. The first set are all without any fancy adjustments, so we've not done any hindsight fiddling or anything like that. This is just based on the actual measures or the actual figures that we had. And we've used sort of, I feel like, as a start point, a fixed assumption of 100 kilograms of SNS in spring. And then we've compared that with a field assessment method. We've also allowed for manures as well. Then sort of standard 0 to 90 SNS measurement in autumn, standard 0 to 90 SNS measurement in the spring, and then adding in a component of additionally available nitrogen into the spring. I hope my builds work here now. If you look at the accuracy first of all, you can see that, remember we were looking for a low negative figure between 0 and minus 20. You can see that the field assessment method, indeed the simple of assumption of 100 kilograms, works just as well as any of the measured SNS approaches, in fact better than the spring SNS. So accuracy-wise, the field assessment method was working pretty well. Precision-wise, the measured values, the measured SNS techniques were working better, giving us higher R-squared figures there. If we take our spring SNS 0 to 90 as our kind of standard approach there without any adjustment, and look at the values there for accuracy, precision, profit foregone, and then compare that with, once we put in a value for additionally available nitrogen, this is the calculated amount of nitrogen that's to be available from mineralisation using the Grow-Hill-Court method. You can see that we are improving our accuracy, going from minus 32 to minus 9. Precision is pretty similar, but we're also improving reducing our profit foregone. So we're losing less profit, as it were, against the harvested SNS technique calculation. If we look at our very best that we could do, which includes spring sampling to 0 to 90, adjustment for additionally available nitrogen, adjustment for leaching, and adjustment for our slope and intercept, we get our accuracy down to about minus 3, our precision up to about 0.57, and our profit foregone down to only £8 a hectare. And all but only 3% of sites had a profit foregone of more than £40 a hectare. But this is what you need to compare it against, and that's the field assessment method, which involves no sampling costs, just really using the book values in RB 209. And the profit foregone there is about £12 a hectare, and only 8% of sites above £40 a hectare. So the difference between the field assessment method and the very, very best we could do with the spring SNS technique was £4 a hectare. And that's before the cost of the SMN sampling. And you can imagine, once you've got the cost of all that in, overall it would be pretty marginal. But of course, we don't use soil mineral nitrogen sampling across all sites. We already have recommendations where to use them. And I've divided the data set up now into normal arable sites and to sites where RB2 and I would recommend that you do the sort of measured SNS approach. So if we take our normal arable sites there, I've just used the profit foregone figures for this comparison. If you compare the field assessment method with the best spring SNS calculation with all the adjustments and tweaks to it, it's less than a £1 a hectare advantage to SMN over the field assessment method. So in our normal arable sites, really, it's just no question it's not going to pay. But on our sites where SMN would be recommended, so that's things like where we've used manures or grassland rotation, high-end veg crops, retentive soils in dry conditions, then it's a slightly bigger advantage to the SMN, something like an £8 a hectare advantage to the measured approach, best SMN approach, compared to the field assessment method. So, how do we distill all that down? Well, the first thing to say is that all the methods of predicting SNS have poor precision. No way of getting around from that. None of them you would class as particularly precise. Field assessment method is best used where the SNS is likely to be moderate or small, and that's basically, in our definition, anywhere where it's likely to be less than about 160 kilos a hectare, less than SNS index 5. So for mineral soils growing arable crops with no grass or manure in the rotation, then the field assessment method is actually pretty good, and that's largely because its accuracy is good. Where is SMN most likely to be beneficial? Well, that is where SNS is likely to be high, or basically where we don't know what it's going to be. And high means above 160, above index 4. So that's most likely to be relevant on sort of deep retentive clay and silt soils in medium to low rainfall areas, either growing high-end crops or receiving manures or something like that. Okay, well, my time's more or less up. Just 4 key messages to leave you with. Whatever you do, whether it's field assessment method or SNS, it's really important that you do go through the process of trying to predict what your SNS is likely to be. Even if it's a case of coming up with the answer, I know what it's likely to be, and it's at a level which doesn't require me to actually do anything specific. That's fine, but you need to go through that process, make a prediction based on one technique or another. As a result of this project, we have clearly clarified which situations SMN-based predictions are likely to perform better than field assessment method, and which situations the field assessment method is actually pretty good. We've also, I think, helped to improve best practice for soil mineral nitrogen sampling. The point about that is, if the technique is done better, we can improve the certainty of the measurement, and that's a very important thing to note. Now, it's clear that SMN testing could be unhelpful and potentially even misleading if you try and use it to fine-tune values in a sort of a largely stable arable kind of mineral soil situation. However, we do think there's a potential for soil mineral nitrogen testing to be used as part of a suite of other techniques and other measures, other indicators, like crop growth, lodging, yield and grain end, to help look at whether individual farms are behaving similarly to the sort of figures in the field assessment method, or maybe slightly outside of that, and in particular to help farmers who've taken on new land, who don't know how the history of the farm at all, and need a bit of a guide to see whether the farm is roughly in line with the field assessment method or not. Then obviously SMN and these other measures can be helpful in achieving that. So there is a role for it going forward. I'd just like to thank all these other organisations for their contribution to the project. Thank you.